Stop time. So, any questions? Yes.
Do you have any comments as to what will happen if school closes?
Is that what you're worried about? Everybody's a little worried.
Like how are assignments in office?
So, there's no plan for the university to close. Obviously, once they cancel hockey, like, what else is there? It's like so we have developed some plans, and we're in the process of building other plans so that if the university will not close, but it's possible that in-person classes will end. So if that happens, you'll be able to enjoy these lectures from the privacy of your home in some way. It's possible we'll be able to do that in a way that you can ask questions. That would be the goal. If not, then it will be like a stream video that you can watch. Assignments and quizzes, they're don't require being here, so those will happen normally. Office hours will not happen, obviously, and labs won't happen, but we're going to try to use the same technology as the lectures so that you can meet with TAs online. Obviously, Piazza will still be there, but that's not ideal, so we'll try. Now, the TAs themselves will be at home, so it creates an interesting situation. So it's our view that it's not ideal, obviously, but that things can proceed relatively okay until the final exam. That's a lot harder for us to do in a way that even closely mimics what normally would happen. So it's possible that if this should happen Monday, it's possible, I don't know, I have no idea. That by the time the final exams came, we'd be able to meet again in person. I think that's probably unlikely. If they do close things, probably close to the exam. So what we will do is everything we can to be fair to you. So our goal will be to ensure that you're not penalized. This means we certainly will have some kind of final exam because for people who didn't do well in the midterm, you're expecting the final to be there. Plus, there's a whole bunch of stuff that needs to get examined. Most likely, it would be a canvas exam where we would ask you to sign an affidavit, legally binding, that you're not cheating, and it would be held at the normal time of the final exam. So that's probably what we'll do. It's obviously not ideal, and certainly leaves the possibility that somebody might cheat. None of you, I know that, but the bias would be if we have a choice between A and B, and A would be fair to you, then we choose A, whatever it is. So in the meantime, don't worry. You're all young. You have nothing to worry about. Think about people like you. What are you dying? It's not, we'll get through this, and hockey will return eventually. It sucks. You're not fan of this sucks because it's just right on the cusp of the playoffs. Anyway, yeah. And the plus side for my son plays midget hockey, and his team just barely didn't make it into the round of playoffs with the Legends provincials. And the provincials were canceled, so he's really happy about that. Okay, so this is the picture. Are you able to? When you said you're worried, I thought you were worried about asynchrony. Because
I'm worried about that too.
Okay, good. You should be worried about that. That stuff's scary, and we're going to talk about it today. So this was the picture. Oops, gotta find it here. Oh, that's it. So this is where we left off last time. These three mechanisms, so built in the hardware, these three different things that are used to manage I/O devices. And we're now going to talk about how they work and how you use them to do various different things. So first, a little bit about how interrupts work. So there are three registers. And I'm simplifying this a little bit, but this is basically how a CPU is actually set up. It's like there are three registers on the CPU, special registers, not general registers, special registers that implement interrupts. So one of them is called the interrupt vector base, which I'm going to abbreviate IVB. So this will be initialized by, when you first start running a program, would be the operating system, before any interrupts can occur, to be a pointer into memory. And this memory is something called, to an array. It's an array of function pointers, and it's called the interrupt vector. And this would be statically initialized so that each entry in the interrupt vector points to a procedure called an interrupt service routine. And every device has a unique entry in this array, and therefore every device has a unique, potentially unique interrupt service routine procedure. The other two registers are set when an interrupt occurs. So there's is device interrupting, and interrupt controller ID. So when some device, so let's say we're going to look at the disk, so disk, the hard drive, let's say its ID is 7, wants to interrupt the CPU. What it does is it's able to access these registers remotely over the bus and set this to 1 and that to 7. And when that happens, now you can see what I'm showing here is if you were to add interrupts to the simple machine simulator, this is what you would add. So you didn't see this loop, but you have spent a lot of time with this procedure, execute. So that's where all the instructions are implemented, where you implemented them. There's also a procedure called fetch that we looked at, but you didn't have to implement anything. We looked at there how instructions are fetched and how the program counter register is changed by the fetch stage. So you remember the program counter always will point to the next instruction to execute. So this loop is the clock. So every time you go through this loop, it's like the clock ticking once. So at the end of the execute stage, the PC points to the next instruction that should execute. And if nothing is interrupting, then you'll just take that PC, go to the fetch stage, fetch that instruction, go to the execute stage, execute it, and repeat. So it's this if statement that's added. Now, in hardware, this would be done in parallel. So we see this as sequential because it's a program step by step by step, but in hardware, we can build things in parallel. So in parallel, with heading to the fetch stage, there's a check of the is device interrupting register. And normally that's 0, so nothing happens. But if it's ever 1, then on this cycle, we're going to switch over to execute the interrupt service routine instead of the program that's currently executing. And that's done doing something that looks a bit like a procedure call. So I'm simplifying it here just to save the register 6. So the first line, the first part of the first line, subtracts 4 from the stack pointer. Right, so this will make room on the stack for the next thing, which is to save R6. So now I can change R6 however I like. And what I'm going to set R6 to is the PC. Just as if I was about to make a jump. So this would be like the GPC, but I don't need the GPC here. I've got the PC directly. And then I'm going to set the PC to whatever is in the interrupt service vector at the index that's stored here. So we go to index 7, and jump, essentially, set the PC to that instruction that jumps there. So it's like inducing a procedure call. There's no call there, it's just, it was in between, in your program, it was a load and an add, and in between those two instructions, now we're gonna do this before the add. It's still waiting here. Now R6 is pointing to it, and we go off to execute the interrupt service routine. Okay. So this interrupt service routine, this interrupt service routine will now run, and at the very end, we have a new instruction, which is called return from interrupt, which we're not going to implement, but every instruction has to have one of these things. And what it does is essentially like a return. So it R6, you'll recall from here, it was the PC of the next instruction to execute, like add. So we'll put that in a temporary, then we're going to restore the old R6 from the stack, add 4 to the stack. So I'm just undoing this part. Clear the interrupting flag. So now use interrupting set back to 0, and then set the PC to T. Okay. So now this would be the execution of an instruction. So this happens in the execute state. So now I come back around here, is device interrupting is false. The PC is what it was before any of this happened, and it will just fetch that instruction. So what happens is your program is running, an interrupt occurs, and in between two instructions, another piece of code runs until it returns from the interrupt. Now, I've left out what happens with protection. So this will happen in the context often of an application program running. The interrupt will take the program into the operating system. It's like a system call. And that return from interrupt will take you back into out of privileged mode into non-privileged mode. But we're not going to talk about that. You learn about that in 3.15. So we can visualize now more accurately the control flow of a system by this picture. So I have the interrupt vector on the far right, pointing to a bunch of pieces of code. They're like procedures, but they're never called in the program, and they never actually return because they have this other kind of way to return, RTI. And your program will run, and the green arrow, so here's a program running. The green arrow represents control flow. An interrupt occurs, it'll go start running this, and then come back. And a key thing to observe here is the interrupt service routine is unrelated, at least not directly related to the program. The program is doing one thing, the interrupts are happening for a different reason. So this creates this interesting kind of weird thing happening, is that your program is running, and in between two instructions of your program, it's like another piece of a program runs. And we'll talk about this, that issues that come up from that next week. We'll talk about threads. Okay. But in the meantime, we're going to look at, well, how do you write a program that can make requests of IO devices and get the data back? That's what we're going to talk about today. Does this picture make sense? We'll come back to this. Okay. All right. So this is just I'll go through it, but it's a diagram of what I just wrote on the board. It's an automation of the diagram I wrote. So here I have some IO controller, say the disk. Well, I have two of them. One, say, is the network device, the other one's the disk. Here's the CPU. For the network controller to interrupt, it sets the ID to 3 and the device interrupting to 1. Then it will run, and later when it's done, it sets it to 0, and then the disk will do this, and so on. And I will say another thing that I left out here is that it's certainly possible that you can have one interrupt, and while you're processing one interrupt, another interrupt occurs. So you actually can, what I've left off here is there's a queue of devices wanting to interrupt. So it isn't like, it's the doorbell, somebody rings the doorbell. If I'm processing that doorbell ring, interrupt service routine is running, somebody else comes to the doorbell, they wait until the doorbell's free again. So this goes back to 0, and then they get to the doorbell. So that's handling the part.
Sorry if I missed this or you mentioned it, but is there a break somewhere in the loop?
A break? No. So how does this end, is what you're asking?
Yeah.
We have an instruction called halt.
Oh,
So this will end when you halt or you unplug the processor. Real processors also will stop when you have the ability to temporarily stop them, to power them down. So if there's no program to run, but you want to be able to run a program should something occur, then the core can go into a low power mode. But this is just the clock ticking. Right? So long as you've got power on your CPU, the clock will tick. Okay. Oh yeah, so this is a key point here. So, care about that, it's the bottom in here. As we talked last time about polling and when it's bad to poll, when it's good to poll, and the reason we introduced interrupts is because if the CPU needs to know about an event in an IO controller, it shouldn't ask it repeatedly. So that was bad to do, like for example, detect mouse movement, because the CPU needs to know pretty much right away when the mouse moves. It has no way to predict when the mouse might move, and asking is really slow. But if you look at what's actually happening here, this is polling. Every single tick of the clock, the CPU is checking this register. But this kind of polling is okay, because that can be done very fast. In fact, as I mentioned, it happens in parallel. So there's actually no cost to execution time to do this kind of polling. So it's kind of a little bit of an interesting way, I think, to think about interrupts, is that we just took polling, the CPU polling the device, and we moved it up to the CPU polling itself, essentially, and then let the device ring the doorbell, and then, so make the expensive thing coming from this direction.
You said that all devices go into a queue, but wouldn't that be like really efficient because everything would have to wait?
No, it's not. It's okay. You talk again. Perfectly fine. Okay, so program dials. But
Oh, no.
okay, I just don't want to. It's. I'll answer.
It's okay.
It's okay. I shouldn't answer questions like that. So I don't want to get into the details of this because our model is that device interrupts, and then the interrupt service routine runs. And what you're concerned about is, well, what if lots of devices are interrupting, and if there needs to be enough CPU time available to process all of the devices. If the devices are able to interrupt at a rate that the CPU can't process them, then your system's hung, and it won't execute. Nothing will happen. It has nothing to do with the queue being inefficient. It has to do with you've got a device that's interrupting too frequently. Does that answer your question?
Yeah.
But don't worry about it. It's not, under normal circumstances, it doesn't happen. Okay, so we're going to look at an example here. Let's say we write a program. This is essentially, and you'll see it evolves into this, is you have a program that you want to access a file or a database. Now, files in particular is implemented by the operating system. We have an operating system. So we're going to go straight down to the idea of reading something from a disk, from a hard drive. Okay. And so that disk is a separate device in the system. So I'm going to eventually draw a timeline here, with time going this way. I have the CPU and I have the disk controller. These are both processors. They're running in parallel, completely independently from each other. Now, sometimes the disk is idle, sometimes the CPU is idle, and sometimes the CPU is running a program. And the only time the disk ever does something is when the CPU asks it to do something. So that's what we're going to look at here. Is that we're going to have the disk perform a read. I'm see the CPU perform a read from the disk. Okay? So that starts with program dial. And later on, I'll show you exactly what that looks like. But it's, the CPU is going to use program dial to tell the disk controller, I want you to read a block. Here's the ID of the block number. Here's how many bytes I want. And when you're all done, here's where I'd like you to put it, an address and memory at the bottom. And when that happens, that causes the disk controller processor to start working on that request. But in the meantime, the CPU is free to do something else. It doesn't have that data yet. It has to wait until step 6 before this whole operation is complete, before it has the data. But because it's independent, there's things it can do in between. And this is why this is asynchrony. Right? So the request that's made is not synchronous. The completion is not synchronous with the CPU. And this is what makes you very afraid. Not afraid of the coronavirus. You should be definitely afraid of this. Okay, so what happens on the I/O controller is when it receives the PIO, it starts processing. It has to get the data from the hard drive, and that takes time. If it's a spinning hard drive, it's going to take 10 to 15 milliseconds to get the data. If it's a solid-state drive, somewhat less than that. At some point, to read complete, it uses DMA to copy the data into main memory at the address that the request said it should go. And then it uses an interrupt to tell the CPU that it's done. So at this point, the disk interrupt service routine runs, interrupting the CPU, whatever it was doing, and it has to handle the completion of that request in some way. So you can look at it in a different way, like this. CPU, PIO, this is the disk controller, that's the disk itself. The yellow thing is the data that's on that you want. The I/O device transfers out to the I/O controller. The I/O controller uses DMA to send it into main memory at the appropriate address. And then it sends an interrupt. So the timeline looks like this. CPU does programmed I/O. And then these two things are now running in parallel, but the question is, what's the CPU doing? It's doing something else. You'll have to figure that out in your program, what it should do. And then this controller is done. So now the CPU has got the data it wanted, and it can kind of continue. Now, for those of you who are in 310, raise your hand if you're in 310. So this is very much like in 310, using AJAX to contact the server. So you do this, and then you make the request, and then some time goes by in parallel with the browser, and then the data arrives later. And this is precisely what we're talking about. Okay. So let's look at an example here of what you might want to do with data from a disk. You can see, it's typically, we write programs as sort of a sequential recipe. It's, first do this, and when that's done, then do this. When that's done, then do this. And so in this case, what you might want to do is these 3 steps is you figure out what data you want, then you go get the data, and then you do something with the data you got. And that's kind of like a skeleton of a program. So you figure out what data you want, and then you go get the data. And then you do something with it. In this case, I'm just going through the data and summing up the value of all of the blocks. DMA stands for correct. All right, and so the problem here is that step, disk read, is asynchronous. It's just the programmed IOs. The CPU isn't going to wait all those many cycles, millions of cycles, while the I/O controller, while the disk controller is working on the request. Because that would be very, very efficient. So the CPU is going to move on to something else. So the problem here is disk read returns immediately. And so, if you place these 3 things on a timeline, we see something unfortunate. So there are these 3 things, 3 events. The first one is disk read, that call returns. The second event is that the data is in memory. And the third event is that loop runs, that it sums up the value of the blocks. So put those down, or talk to each other about where they would be on this timeline, those 3 events. Okay, so where is disk read returns? Where is that event? Stop me when I get to it. Stop me. You have to say stop. Stop. Right, it's right there. And it's the end of that green line, which is the key point here, is that the disk read it's not really disk read, it's sort of the wrong name. It's like start the disk read. And that's the CPU's entire job, is just to start it. And now the I/O controller's job is to finish it. Where on the timeline is the second item? The data is in memory. All right, so it's when the DMA occurs, it's the end of the blue line. And so now where is the loop? Well, the loop will execute right after disk read return. So the loop is going to execute right here. But where do we want the loop to execute? It has to be after this, because the data that we want to sum isn't in memory until that point. So this is an error because the loop runs too early. So in fact, we can just rearrange based upon the actual time these would occur. It's like this. I would ask for the data, and then I would use the data, and then I would get the data. And obviously that doesn't work. So this introduces a need to have a different kind of programming. So this is asynchronous programming. And you've done this kind of thing before that I'm going to show you before in Java. If you wrote code for Java FX or Swing to handle user interaction events, like on mouse click or something like this, and you've done it in 310, I'll use promises, but you did it in 310 with AJAX, okay? So it's not necessarily new, and it is to most of you, and it is a standard alternative way of programming to procedure calls. So procedure calls is like one way you can write programs, and using asynchronous callbacks, which we'll talk about, is another way. Or you can combine them, which is what really you have to do, unless we add some additional abstractions, which is what we're going to do next week. All right, so I've got these two pieces of code. The disk read that initiates the request. It determines, so there's the buff. It tells in the read, that's where the data should go. So it's going to use that for the DMA, and then it tells it what it wants. And then this runs for a while, and then this piece of code, will run as the result of the interrupt. Okay, that's what has to happen. There's an event, the interrupt, that tells the CPU that the data is there, and it's sometime after that, so that has to cause this code to run. And so these two things are asynchronous, they're not tied together. In fact, this code will make it a procedure, but you never call this procedure in your program. It's going to be called by the interrupt service routine, by the event. Okay? So we'll take that piece of code, everything that should run after the event finishes, and make it a procedure, and then we'll add a function pointer to the disk read. And we'll pass that value to that parameter. So we're going to tell the disk read now, okay, here's where the data should go, here's the data I want, and when the interrupt occurs, here's the procedure you should call. So then, it's like this, here's compute sum, that's a parameter. Okay, we sometimes call that registering a handler for the event. But you don't have to worry about that term. It's just we're going to save somewhere that pointer to that code. And then these things happen as before. And then when the interrupt occurs, beautiful animation, and that will run. So if you think about this, like draw a little picture of it. I've got a procedure now. This procedure will have parameters usually, and we'll have to pass those parameters to discrete as well. But I'm going to just leave those off. So this is the code that will run when the interrupt is done. And I never call this. I have another piece of code that does the discrete. And I pass in the parameters there, and then one of the parameters is compute zone. Now what discrete does F is the completion routine. Is it's going to save that. Here I'm just going to save it in global variables. So I'll have some global variable that's a function pointer. I'll just call it C. And so what it does, it says C equals F. Okay, so in this case, C now is a pointer to that code. And then do the PIOs. And then return. And then everything that comes after discrete now is just stuff that will run before you know that the data is in there. So it has to be independent of this request. Or you can't use the data here. But at some point the interrupt occurs. Okay, so here we have the interrupt service, the interrupt vector. And it points to the interrupt service routine for the disk. And it's going to do some things. And one of the things it's going to do is say, well, let me check that global variable. And if it's set, then I'll call that procedure and then set it to null. In a simplified form. So the interrupt occurs. The CPU interrupts whatever it's doing. Right? It's some in the execution sometime way after this. Whatever it's doing is interrupted. To run this procedure, the procedure looks at that global variable, and if it's pointing to something, it runs whatever's pointing. And so compute sum, if we looked at its stack, the bottom of its stack is an interrupt service routine. Compute sum. Right? The interrupt service routine runs. I didn't show it's going to switch to a new stack. And then it calls compute sum. When compute sum returns, it just returns back the interrupt's over. So there's nothing that can happen on the return path from compute sum. It's just going to go back to running the regular program. And that's going to be important.
So in this case, originally we wanted like the buffer thing to be like in the sum. So how do we get the sum variable back?
So you're asking, how does compute sum know the address?
No, so does sum have to be like a global variable, or like how does it get returned if we're no longer?
Yeah, so that's the problem that we're going to talk about, is you can't return it. Now, in terms of input parameters, you can add input parameters here, and then they'll be stored. I just have this one global variable. This will actually be a struct, and you can provide parameters, input parameters. But the problem that we have to deal with, and this is what we're talking about right now, is it can't return anything. And it can't. So we'll have to do that in a different way. Okay, that's what we're going to talk about.
So if so during the time when the disk is writing to the RAM,
Yeah.
is it not possible to access any of that memory and RAM that, like, say, like it's like a huge file?
Yeah.
Can that for loop be executed while being written
Yeah.
to RAM?
So this is a good observation, is that the data is actually in memory before the interrupt. Right? Because the steps are PIO, find the data. This takes a long time. Start the DMA. When the DMA is all done, interrupt. So at the point of the interrupt, you know for sure all the data is there. But before the interrupt, some of the data might be there. And if you had some way to know, and you really wanted to get started on it early, and maybe you didn't care about it, you're gonna end up probably wasting CPU time to figure this out. But if you had some way to know whether the data was there, and how much it was there, then you could avoid the interrupt. The interrupt just exists as an efficient way to let you know that the data is there for sure. So the normal way that you write programs in this environment is that you would have the CPU doing something else useful until the interrupt occurs.
There's no way you could have like a double layer of interrupts where it checks to see if all the memories are written, or all the memories are written in the RAM, and then pauses and lets the CPU do something else, checks it, and checks again each time something new is written.
Well, so what you're saying is that if you have a very, very large transfer, or a long running operation, would it make sense to batch it? So that you do a little bit and then interrupt a little bit more and then interrupt. Yeah, it might, and that you can do that with this mechanism. You just have multiple interrupts, each one for each segment of this. It turns out that the memory transfer is not the slow part. So once normally the data is going to get staged, and then so there's a big delay, and then the transfer to memory happens basically. But yeah, it's a really good observation. What you're thinking about is something called pipeline. You don't want to have things wait until one thing is completely over before you start the second one. One thing and the second one. If possibly, you could overlap them a little bit. And we're going to look at a version of this when we look at asynchronous programming with multiple requests. So this actually becomes quite important, but we won't see that until the end of next week. All right, so back to this. We have to deal with this problem that disk read can't return anything. Compute sum can't return anything. But first, I'm going to give you the details. You don't really need to know this, but this makes it concrete, hopefully, how this is implemented. So this slide shows the PIO side of the implementation, and the next slide shows the interrupt side of the implementation. So disk read does this. It first takes, so there's a struct. This struct describes the protocol that the disk read controller has set up for how the CPU should talk to it. Okay? So this disk read, which has the parameters buff, block number, number of bytes, and the completion routine, takes the disk's address, which is a constant. This is its PIO memory address, 800000000 or something like this. Oh, it's actually up there, 8000100. And has this pointer DC pointed. So now the four stores that are listed below are going to be programmed I/O messages sent to the controller, because that address is in the memory mapped space, not in actual real memory. And the protocol says, well, the first thing you do is tell me what the operation is. It'll be a read and write different things. The next thing you do is you give me the DMA address, so I know where to put the data. Next thing is you tell me which block you want, and finally tell me how many bytes you want. Okay? So that's a message. Those 4 words are a message that's sent to the I/O controller, and then disk read just returns. It does nothing else. So its total running time is the running time to do 4 programmed I/O stores. And then this is all about handling the interrupt. So if you look at the very top here, this is sort of the static stuff, is that the very first line defines an array, the interrupt vector. So that's just an array of function pointers. The next thing is says, well, we're just picking 4 to be the disk's interrupt ID, device ID. And then we'll set interrupt vector entry 4 to point to this procedure that's shown at the bottom of the slide called disk ISR. So this is the code that will run every time there's a disk interrupt as a result of setting that up. And then, so this is back to disk read again. The PIOs are below this. This line was grayed out in the previous slide. So what this is going to do is store onto a queue a record, a struct that contains those 4 things. What what the completion routine is, what to do when it's all done, so that's going to be this thing, and the buffer, the blocks, and everything else, which will become parameters to that completion routine. And then when the interrupt happens and this GuiSR runs, it's going to dequeue that information. And what it will get is a pointer to some code that's being handling. So it's going to call that procedure, and it's going to provide these three parameters. So these would be the three parameters right here. So they do this. So now to this problem of returning things. So in a program, probably you'd have something like this. Some disk data, you go through the loop, sum it all up, and then you return the value. We had to change it so that compute sum, the loop, is in a separate procedure, and I told you that procedure can't return anything because it's not being called from your program, it's being called from the interrupt service user. So how do we fix this problem? What if I want to do something like this, or I just simply want to sum all the data, sum disk data, get the sum, and print it? How would you do it in the asynchronous case? So this is the asynchronous code. I've added not and free on the buffer, but that doesn't matter. Just go through the loop. How would you do this? Let's talk about that for 1 minute. The thing I want to print is this sum. And where in the code do I know the value of sum?
When the interruption called.
I know it right after the loop finishes executing. Right, so if you look at the loop and compute sum, when that loop is done, just before the free, I know the value. And where is it stored? In a local variable. So when will I no longer know the value of the sum? As soon as compute sum returns. So the only place I know what that number is in the program is right after the loop. So if I'm going to do something, I have to do it right there. And so the solution is that you have to move everything that you want to do after you have the sum into the completion path. So here, what that means is putting the print right after the loop. And we'll look at this. I'll just go right to the next slide to show you this. This is the bottom part here is generalizes that so I can call anything. So it just basically the idea is, well, I'll compute the sum, and then I'll call some procedure that'll handle everything else as a result of that. And we'll come back to how this creates a problem. But leaving today, the basic idea of asynchronous programming, the way it's different from the procedure call programming, which goes sort of like a pipeline. You say, okay, do this thing, and when it's all done, return, and then do the next thing. And you can follow the control flow by just looking at the procedure calls, even procedure calls, synchronous. With asynchronous program, it's like this. You say, okay, ask for something, and then everything in the program that has to happen after that point will be caused to run by the event flag. And so you'll have a whole bunch of stuff. It's not just printing. Maybe the entire program will depend upon that value. Maybe what you did was say, read the sum, and then that's the input to the next thing. Do something, that's the input to the next thing. In that case, that whole entire remainder of the program you called in some way from the completion. So have a great weekend. Don't worry about things.